Hi children, in last class we discussed about bases, their properties and some important applications of bases. So in continuation to that chapter acids, bases and salts, we are going to discuss today the strength of acid and basic solutions pH scale. So if you consider water, so generally water slightly ionized into H plus and OH minus ions. So water contains small number of H plus and small number of OH minus ions. How these H plus OH minus ions are formed? They are formed by the dissociation of water. But this dissociation occurs only to a small extent. So that is the reason why these two ions existing in minute quantities, okay, they are not significant. In pure water, the concentration of H plus ions and OH minus ions are equal, though they are formed in small quantities, their concentrations are equal. So due to this due to the equal number of H plus and OH minus ions, water exists as neutral solvent. So it's neither acidic nor basic. Suppose if we add an acid to water, what happens? Acids produce H plus ions in water. So when an acid is added to water, the concentration of H plus ions in water increases. Say for example HCl. If it is added to water, what happens? It ionizes to H plus and Cl minus ions, right? So because of the newly produced H plus ions from H plus, the concentration of H plus ion in water is increased due to the addition of acid. So acid solutions have excess hydrogen ions than hydroxide ions. So acid solutions have excess H plus ions than OH minus ions. Similarly, if we add bases to water, what happens? Bases produce hydroxide ions, OH minus ions in water. So when a base is added to water, the concentration of OH minus ion in water increases, right? So like that, say for example NaOH. If it is added to water, what happens? It ionizes to Na plus and OH minus. So this increases the OH minus ions concentration in water. So that is the reason why basic solutions are having less number of hydrogen ions than the hydroxide ions. So in acidic solutions, the concentration of H plus is more than concentration of OH minus. In basic solution, concentration of H plus is less than the concentration of OH minus, whereas in acidic solutions, concentration of H plus is greater than concentration of OH minus. So this is the thing. So now we are going into, so what have we discussed? In case of water, the concentration of H plus ion and OH minus ions are equal, so that is neither acidic nor basic. In acidic solutions, the concentration of H plus ions is more. So because of the presence of excess H plus ions, they are acidic in nature. In basic solutions, the concentration of OH minus ion is greater than concentration of H plus, right? Then in 1999, in 1909, a scientist called Sorensen, he devised a scale, right, on which the strength of acids solutions as well as basic solutions could be represented, making use of hydrogen ion concentrations present in them. That scale is called pH scale. So what is pH scale? pH scale is a scale that is used to measure the strength of acidic or basic solutions, right? And this scale works making use of hydrogen ion concentrations present in the solutions, right? So pH scale is a scale used to measure the strength of acids and basic solutions. So by using pH scale, we can measure the strength of acids or bases quantitatively. So quantitatively means by the quantity of H plus ions can be measured. The quantity of H plus ions can be measured. So pH scale generally consisting of 0 to 14. pH scale consisting of 0 to 14. So if a solution is having pH 7, that solution is called neutral solution. Solutions having pH less than 7, that means 0, 1, 2, 3, 4, 5, 6 are called acidic solutions, and pH the solutions containing pH more than 7, that means 8, 9, 10, 11, 12, 13, 14 are called alkaline solution. So as we move away from the middle number 7, the acidic or basic nature increases. Suppose if we move towards extreme left hand, at 0 the solutions are more acidic, and pH with 17 14 are more basic or alkaline in nature. In pH, P stands for potenz. Potenz means power in German language. Potenz means power. So power of H plus ions. The pH scale lies between 0 to 14. Please note that pH is a pure number. It has no units, right? So it has no units, right? Because it's a number. This number helps us to measure the strength of an acid or a base in a quantitative way, not qualitative way, in a quantitative way. Next, so say for example a solution is having pH 7. So what does it mean? Right? pH equal to 7 means the solution is neutral. So solution is neutral means the H plus ion concentration and OH minus ion concentration present in this solution is equal, right? In that case only it is neutral. So substance having pH 7 will have no effect on litmus or any other indicator. Acids or bases can have effect on litmus paper, right? Acids turn blue litmus to red, bases turn red litmus to blue, but neutral solutions do not have effect on litmus. So when pH equal to 7, it means neutral solution. Why they are neutral? Why those solutions are neutral? Because the concentration of H plus ion and OH minus ion present in them is equal. Say for example, if pH less than 7, what does it mean? pH less than 7 means the solution is said to be acidic in nature. It means it contains more number of H plus ions than OH minus ions. So the concentration of H plus is greater than the concentration of OH minus. So in such case, these solutions are having acidic in nature. More acidic solutions will have a low pH value. Say for example, solutions below pH 7 are acidic. In that solutions, again, if we compare a solution of pH 1 with a solution of pH 4, definitely pH 1 is more acidic than a solution with pH 4. So lower the pH value, higher the acidic nature. Higher the pH value, lower the acidic nature. Why this happens? Because actually the formula of pH is not there, not mentioned in our syllabus. So if you look at the formula, pH equal to minus logarithm of H plus ion concentration. Minus pH equal to minus log of H plus. So the relationship between pH and concentration of H plus is negative log. So what happens if you increase the H plus concentration? The pH value decreases. If you decrease the H plus concentration, the pH value increases. So that is the reason why that is not in our syllabus. So as pH increases, acidic character decreases. pH decreases, acidic character increases. So among the acidic solutions with pH 0, 1, 2, 3 are considered as strong acids, right? So pH 0, 1, 2, 3 are called strong acids. For example, HCl solution is having a pH of 1. Lemon juice is having a pH of 2.5, right? Next, solutions with pH equal to 4, 5, 6 are considered as weak acids, right? No doubt, solutions having pH less than 7 are acids. So, among the acids, strong acids are having pH 0 to 3. Weak acids are having pH 4 to 6. For example, if you take vinegar, acetic acid is the constituent component of vinegar. It is having a pH nearly 4 to 4.2. Coffee is having a pH of coffee that we drink every day, that is having a pH of 5.0. So coffee is a weak acid, acetic acid is also weak acid. Similarly, what we call that, there are some other weak acids are there. For example, tomato juice, that is also weak acid, right? Soft drinks that we drink, they are also weak acids. So what is the important point here? Lower the pH, stronger the acid. Why? That is due to the relationship pH equal to minus logarithm of H plus. So all solutions having pH less than 7 are acidic in nature, and hence they turn blue litmus into red. So which of the following solution turns blue litmus into red? Option A, pH equal to 0. Option B, pH equal to 7. Option C, pH equal to 9. Option D, pH equal to 14, right? So the acidic solutions only turn blue litmus to red. So acidic solutions are having pH less than 7. The option could be 0, option A, right? So all the solutions having, a solution is having pH less than 7, all the solutions having pH less than 7 are acidic in nature, and hence they turn blue litmus to red, and they also turn methyl orange indicator to red. Actually, we are going to discuss about methyl orange in the indicators concept. So acids turn methyl orange indicator to red color. So a solution which pH greater than 7 is alkaline in nature. It contains less number of H plus ions than OH minus ions. In other words, the number of OH minus ions is more than the H plus ions. More basic solution will have higher pH value. More basic solution will have higher pH value. But in case of acids, higher the pH, lower the acidity. Lower the pH, stronger the acid. Less basic solution will have lower pH value. So, for example, for bases, right, the pH lies between 7 to 14, right? Bases having pH 8, 9, 10 are said to be weak bases, and bases having pH above 10, that means 11, 12, 13 are said to be strong bases. So for example, a solution with pH 14 is more basic than a solution with pH 10. It is exactly contrary to acids. In case of acids, a strong acid is having low pH, a weak acid is having high pH. But in case of bases, a strong base is having high pH and a weak base is having low pH value. So alkaline solutions with pH 8, 9, 10 are considered as weak bases. For example, magnesium hydroxide. This is called milk of magnesia. Milk of magnesia is having a pH of 10.5. That means it's a weak base. Sodium bicarbonate solution is also having pH of 8.5. This is also a weak base. Alkaline solutions with pH more than 11, 12, 13, 14 are considered as strong bases. Example, sodium hydroxide is having pH 13 to 14. So concentrated solutions are having pH 14, diluted solutions are having pH 13. So higher the pH, stronger the base, right? And in case of acids, lower the pH, stronger the acid. So all the solutions having pH more than 7 are basic in nature, they turn red litmus into blue, and they also turn phenolphthalein indicator into pink color. Right? This phenolphthalein is also going to be covered in the indicators concept. Phenolphthalein indicator is very important indicator as far as bases are concerned, because phenolphthalein indicator shows colorless. It has no color in acidic solution, whereas it shows pink color in the basic solutions. So pH of some substances. So look at this scale carefully. Okay, this is the pH scale. So it is graduated between 0 to 14, and at the middle of the scale 7. Solutions having pH 7 are said to be neutral, right? And solutions having pH less than 7, so left hand side, are acidic solutions. If you go from 7 to 0, the acidic nature increases, increasing acidic nature increases. In other words, H plus concentration is also increases. So pH 0, 1, 2, 3 solutions are strong acids. Having pH 4, 5, 6 are weak acids. Similarly, if we move right hand side of 7, from 7 to 8, 9, 10, 11 and so on, the basic nature increases, and pH solutions having pH 11, 12, 13, 14 are strong bases, and solutions having pH between 7 to 10 are weak bases, right? So if we move in right hand side direction from pH 7, you are into the basic side. If we move left hand side of the pH neutral pH 7, then you are going towards acidic side. If we move to far extreme left, then you will encounter strong acids. If we move extreme right, you will encounter strong bases. Okay, this is the table of some important substances and their pH values, respective pH values. See, first one, hydrochloric acid, concentrated. Concentrated, what is the difference between concentrated and dilute hydrochloric acid? So, in dilute hydrochloric acid, the number of H plus ions are less when compared to the concentrated HCl. So since concentrated hydrochloric is having more number of H plus ions, the pH value is less. More number of H plus ions means strong acid. Strong acid is having less pH. Dilute hydrochloric acid having small number of H plus ions and compared to concentrated hydrochloric acid. Hence, its pH value is more than concentrated hydrochloric acid. So anyway, concentrated hydrochloric acid, whether it is diluted or concentrated, hydrochloric acid, whether it is concentrated or diluted, it is having a pH of 0 to 1. Then very important thing, gastric juices. So gastric juice that is present in our digestive system is also hydrochloric acid. Its pH is very important, 1.4. This is also strong acid. So this much of strong acid is essential to digest the proteins that we eat in our food, right? And next, lemon juice, it is having a pH of 2.5. So by looking at this value, one can say lemon juice is also strong acid. Why? The acids having pH 0 to 3 are called strong acids. So lemon juice with pH 2.5 is also strong acid. And vinegar, consisted, the active constituent of vinegar is acetic acid. It is having a pH of 4.0. pH 4.0 indicates it's a weak acid, because from 0 to solutions having pH value 0 to 3 are only strong acids, and pH value above 4 are generally weak acids. Similarly, tomato juice is a weak acid with pH 4.1, and coffee is again a weak acid with pH 5.0. Soft drinks means soda and all the things. Carbonated water, they contain carbonated water, that is CO2. CO2 is a non-metallic acid, right? Non-metallic oxide. Non-metallic oxides are acidic. That is the reason why soda is also acidic with pH of 6.0. And coming to milk, milk is also acidic, but mild acidic with pH 6.5. This is due to the presence of lactic acid in the milk, an organic weak acid. And pure water. Pure water is having a pH of 7.0. It is neutral. So milk is also weak acid, right? So pH 0 to 3, strong acid. pH 4 to 7, weak acids. pH 7, neutral, right? Then coming to bases table. So saliva. So saliva before meals is having a pH of 7.4. That means it's a weak base. And saliva after meals is having pH 5.8, which is less than 7. Hence it's a acid, and among acids it is weak acid because its pH is more between 4 to 7. So that is the beauty in this. And blood, right? So you have to think why saliva is having different pH values before and after meals, and you have to answer me this question. If you are unable to do, I'll answer you. Blood. So blood is having a pH of 7.4, human blood. And eggs. So blood is weak base, right? And eggs are also having pH 7.8, weak base. Baking soda, sodium bicarbonate, baking soda is also a weak base, right? With pH 8.5. And washing soda, Na2CO3, sodium carbonate is also a weak base, so pH 9.0. And milk of magnesia is also weak base with 10.5, or magnesium hydroxide is called milk of magnesia. And our household ammonia, which is used for toilet cleanings, is having, it's a moderately strong base with 11.6. And dilute sodium hydroxide, concentrated sodium hydroxide, they are strong bases with pH values 13 to 7. So here pH 7 to 10 are weak bases, pH 11 to 14 are strong bases. So here some important questions are there. Blood. What is the pH of blood? And what could be the pH of saliva, gastric juice, and milk? These are very, very important. Lemon water. Okay, you have to make note of this. So this table covers pH of various substances. In this table, pHs based on the pH, substances are categorized like strong acids and weak acids, strong acids and strong base, and neutral. Pure water is the neutral solvent. So next concept is universal indicator. So what is an universal indicator? So then what is an indicator first? Indicator is an organic substance or organic dye which is used to determine whether a solution is acidic or basic. So then what is universal indicator? So normal indicator is having a limitation. It just identifies whether a given compound is acidic or basic, but it cannot distinguish two acidic solutions. That means it cannot distinguish between strong acid and strong base. It cannot distinguish between weak acid and weak base. That is the disadvantage of normal indicator. Whereas if you consider a universal indicator, the speciality of universal indicator is, unlike normal indicator, it can differentiate a strong acid from strong base and a weak acid from weak base. In other words, it can be used to measure the strength of acids and bases, right? So it is made, how it is, what it is made up of. Generally, universal indicator is a mixture of several indicators, many different indicators, which gives different colors at different pH values. So the characteristic property of this universal indicator is, this indicator gives different colors at different pH values. Say for example, at pH 1 the color is red, at pH 4 the color is orange, At pH 7, the color is green. At pH 10, the color is blue. At pH 14, the color is violet. Like this. So you need not to remember all the colors. Just I am giving an example. Depending upon the pH, universal indicator exhibits different colors. So by comparing the color of the color produced by the indicator and comparing the color with the given chart, one can say the pH of a given solution. So universal indicator is a mixture of many different indicators which gives different colors at different pH values. It is not possible to measure the strength of an acid or basic solution using normal indicator. As we discussed, normal indicator is having very limited applicability. It just used like litmus. It just used to check whether a solution is acidic or basic, only for screening. However, the strength of an acid or base can be measured by using an universal indicator. So what is the mechanism of this universal indicator? See, we'll go through this. When an acid or basic solution is added to the universal indicator, the indicator produces a new color. The color produced by the indicator is used to find the pH value of acid or base solution by matching with the color of the pH color chart. So there is an indicator paper, universal indicator paper, and there is a color chart, right? Like this, like this color chart is there. I can't write the colors here, right? So at pH 1 the color is red, at pH 4 to 5 the color is orange, at pH 7 it is green, at pH 10 to 11 it is blue, at pH 14 it is violet. So like this, a pH paper is provided, a universal pH paper. It is showing different colors at different pHs. So what we do, for example, a solution of unknown pH is provided and asked you, and you are given a pH paper also, universal pH paper, and asked for its pH. Then what we do, simply we put a drop of that solution on the pH paper and observe the color, what it is obtained. So match that color with the pH color chart. If it matches with pH 5, then the matches with color red, then pH is 1. If matches with color 14, pH is violet. If matches with pH 5, then color is matches with color orange, pH is 5, like that. So knowing the pH value, we can find out whether a given solution is strong acid or weak acid, strong base or a weak base. Say for example, universal pH paper has shown pH of 5. What does it mean? So the sample is a weak acid, right? If it shows green color, then what is the nature of the solution? So when it's shown green color corresponds to a pH of 7, then the solution is having pH 7. For example, if your given solution has given violet color with pH paper, then what could be the pH of that solution? It is 14, because violet color corresponds to pH 14, like that. So by using the universal indicator and the pH chart, one can find pH of a given solution. In other words, strength of a given acidic or basic solution. So here I am giving only 3 examples. All the colors are not important. Only 3 colors you have to remember. So what is the color for neutral? What is the color for acidic? What is the color from bases in case of universal indicator? Alright, it is also good if you remember color for weak acids as well as weak bases. So neutral solutions. Neutral solutions or neutral substances produces green color with universal indicator. So now I am asking a question. So what could be the color of universal pH paper if a drop of pure water is introduced on it? Right? Pure water is neutral, right? Its pH is 7, right? So pH 7 corresponds to which color? Green color. Therefore, pure water or neutral solutions produce green color with pH paper, universal pH paper. Acidic solutions produce red color, that is strong acidic solutions produce red color, and weak acids produce orange color with universal indicator. Strong acids having a pH of 0 to 3, weak acids having a pH range of 4 to 7. Right. Similarly, strong bases produces violet color. Strong bases produces violet color, and weak solutions produces blue color. So pH 14 is strong, hence it produces violet color. Weak bases produces blue color. So with universal indicator. Okay, that's it for today's class. So I am going to summarize what have you learned so far. So we have learned today what is a pH scale. You know, before that, water is neutral. It is having equal number of H plus and OH minus ions, so it is neutral. But whenever an acid puts in water, it forms an acid solution. Acids produces H plus ions. So because of the newly formed H plus ions, the concentration of H plus ions is more. Hence, in acidic solutions, H plus concentration is more than OH minus. Similarly, in basic solutions, bases produces hydroxide ions in water. That is the reason why concentration of OH minus ion is greater than H plus ion, or H plus ion is less than OH minus ion. So what is pH scale? In order to measure the strength of acids and bases in terms of H plus ion concentration, a scale was introduced by a scientist called Sorensen. That scale is called pH scale. So by using pH scale, one can measure the strength of acids and bases quantitatively. pH scale has no units and it consisting of numbers from 0 to 14. In pH, P stands for potenge. It means German. It means power in German. So this scale lies between 0 to 14. pH equal to 7 means neutral. It is having equal number of H plus and OH minus ion. It does not change the color of litmus paper. And pH less than 7 means a solution is said to be acidic in nature. This contains more number of H plus ions than OH minus ions. Right? The solution is said to be acidic. And a more acidic solution have less pH value. Less acidic solution have more pH value. For example, pH 1 is more acidic than pH 4. Solutions with pH 0 to 3 are called strong acids. Solutions with pH 4 to 6 are considered as weak acids. Solutions having pH less than lower the pH, stronger the acid, right? And solutions having pH greater than 7 are called bases. They are containing less number of H plus ions than OH minus ions, right? So a more basic solution have high pH value, a less basic solution have low pH value. Solution of having pH 14 is more basic than solution pH 10. So among alkaline solutions, pHs 7, 8, 9, 10 are said to be weak bases, and pH 11, 12, 13, 14 are said to be strong bases. So higher the pH, stronger the base. Substances having basic nature turn red litmus to blue. So this is the table of things having different pHs, right? Among these, gastric juice strong acid, lemon juice strong acid, milk weak acid, saliva before meals weak acid, after meals strong acid. You should know. You should explain me why it is like this. And blood is having pH 7.4. And finally, universal indicator. So universal indicator is used to measure the strength of acids and bases, right? Unlike normal indicators, it differentiates weak acids from strong acids as well as weak bases from strong bases. Then what we do, we simply take a universal pH paper and we simply put solution of whose pH to be determined. So based on the color change, we are going to match the color with the pH chart and find the corresponding pH. So pH for solutions having pH 7, the color is neutral. for solutions having pH 1, strong acids, color is red. For weak acids, color is orange. For strong bases, color is violet. For weak bases, color is blue. So that's it for today. And after this class, go through the lecture notes that is going to be shared through you online. Thank you so much. Stay safe, stay home, stay safe. Thank you.